So, hello everyone again. This is lecture 3 part 3 of alternating current. In the previous lecture we have completed with the phase diagram solution of the AC source applied to a series LCR circuit. We have started with the analytical solution understanding of this topic only. Let us complete that topic. Let us try to understand what is the difference being observed regarding phase difference solution, phase diagram solution and analytical solution, and after that we will move on to the new subtopic which is resonance. So, this is lecture 3 part 3 of alternating current. I am Sameer Lavankar. Let us begin our discussion. So, currently a course outline for you. We are on the 6th topic, that is AC voltage applied to a series LCR circuit. We have completed with the introduction part, AC voltage applied to a resistor, representation of AC current and voltage by rotating vectors, AC voltage applied to an inductor, AC voltage applied to a capacitor, and currently we are on the 6th topic. In this it is divided into 2 topics. Basically, to understand the solution we are trying to understand first regarding phase diagram solution, and then we now currently we are moving to analytical solution. Okay, so this was how we started with the analytical solution. Okay, so let me first of all substitute everything. So after substitution we will finally obtain what? We will finally obtain nothing but equal to L in brackets. So for dt q by dt square, what we can write? We can write basically it is nothing but minus qm omega square sine of omega t plus theta next thing is for dq by dt. So, it is nothing but r multiplied by in the place of dq by dt can write this as equal to qm omega cos of omega t plus theta, and next thing is regarding your q by c, correct. So, it is nothing but q by c. So, it is 1 upon c into q will give you qm sine of omega t plus theta, correct. Now, let us try to understand this more. In the place of if I try to rearrange this equation, what can I obtain? We can obtain directly that, let us suppose omega L, omega and omega, correct. So, if I try to change it as equal to omega L, so we know that as x L is nothing but equal to omega L and x c is nothing but equal to 1 upon omega c. So, we can just write or divide omega and omega here, and similarly omega and omega here, correct. So, we will finally obtain the equation as, we can just, I will write the equation directly. So, we will obtain the equation as qm into omega into r cos omega t plus theta plus x c minus x l into sine of omega t plus theta. Okay. So, simple substitution is only done. I have explained how that substitution is also done, and then finally rearranging the equation and removing out qm omega, we got the equation as nothing but equal to, so this is not 0, this is basically v, this is equal to Vm sin omega t. Okay. Now, let us try to multiply and divide z also here. Okay. So, let me write that because it needs remembering. So, multiplying and dividing by under root of r square plus x c minus x l whole square, which is equal to z, we get qm omega z into r by z. Now, look at the bracket very carefully, cos omega t plus theta plus x c minus x l divided by z into sine of omega t plus theta, correct, which is nothing but equal to Vm sine of omega t. Okay. So, if you look at this very carefully and let us say I denote, let us say let r by z is nothing but equal to cos of phi. Okay. So, if this is said as cos phi, we can directly say that cos phi cos omega t plus theta is equal plus sin phi sin omega t plus theta. So, this is little nothing but a trigonometric identity. Sin phi. So, therefore, just simplifying we will obtain nothing but equal to V m is nothing but equal to q m omega into z. Okay. So, basically this will be nothing but equal to cos of omega t plus theta minus phi, because the trigonometric identity states that. So, it is like cos a cos b plus sin a sin b is nothing but equal to cos of b minus a. Okay. So, let me write that. So, it is nothing but cos of omega t plus theta minus phi. Okay. So, I hope you understood this very carefully. How is this thing obtained? Anything more to explain here? So, basically this is okay. So, this okay. So, this will be V here, okay, which is equal to V m sin omega t, and yes, okay, fine. So, this is the equation obtained. So, this is the equation obtained after this. So, basically now just comparing both the sides. So, let me first write the equation again. So, what was the equation we obtained? We basically obtained q m omega z into q m omega z into cos of omega t plus theta minus phi, which is equal to V m sin of omega t, correct. So, now using comparison, comparing both sides, what we can say, we can even write sin omega t in terms of cos omega t and directly equate that form also. So, basically amplitude is also equated and the sin form or cos form is also equated. So, comparing two sides, we get first of all V m. What is the value of V m? V m is nothing but equal to q m omega z, and similarly for the cos form or sin form, what we can rightly say? We can say that theta minus phi is nothing but equal to minus pi by 2, okay, because omega t will get cancelled and cos omega t will change its form into nothing but equal to omega t minus pi by 2. Okay. So, we can directly write this as nothing but equal to V m cos of omega t minus pi by 2. Okay. So, simple trigonometry, I am applying just simple trigonometric identities here. So, therefore, we will get V m is nothing but equal to q m omega z. Also, I can write this as equal to nothing but equal to I m into z, right. So, therefore, what we can obtain, I m is nothing but equal to q m into omega, correct. And as theta minus phi is equal to minus phi by 2, or in another form we can write theta is nothing but equal to phi minus pi by 2. Okay. So, therefore, now okay, in the previous, what was the simple equation which we used for q? I think for q we used, yes. So, for assumption of q, this was the equation which was obtained, that is q is equal to q m sin omega t plus theta. And what was the current being obtained? Current was obtained as equal to q m omega cos omega t plus theta. So, let us use this equation number. What was the equation number? Equation number was 3. So, using that equation number 3, what we can directly say, that what is I? I is nothing but equal to, using equation number 3, right. So, I is nothing but equal to dq by dt, and therefore, what we can obtain, this is nothing but equal to q m omega cos of omega t plus theta, right. So, in the place of q m omega, I can write it as equal to I m, and cos of omega t plus theta, in the place of theta, I can write this as equal to phi minus pi by 2, and hence this can also be written as equal to nothing but I m sin of omega t plus phi. Okay. So, I hope this is clear to you how I am trying to obtain everything here. What is this value of I m? Im will be nothing but equal to Vm by capital Z, which is nothing but equal to Vm upon under root of R square plus Xc minus Xl whole square. What is phi here? Phi is nothing but equal to tan inverse Xc minus Xl by capital R. Okay. So, that is how we obtained this thing. This last two equations are directly obtained using the phasor diagram solution only. Okay. So, that is how the analytical solution for the amplitude and the phase of the current in the circuit agrees with the obtained by technique of phasors. Okay. So, that is how this thing was done, just revising everything which I did. So, basically we started with this voltage equation here. Let me change the pen color. So, we started with this voltage equation here. How we obtained this voltage equation? Using simple Kirchhoff's loop rule. So, the Kirchhoff's loop rule basically states that the voltage applied by the AC source is nothing but divided into three different devices. First is regarding the L, that is inductor, then R is resistor and C is capacitor. The amount of voltage for an inductor is L di by dt, for resistor it is IR, and for capacitor it is Q by C. So, basically L di by dt plus IR plus Q by C is equal to small v. We know that I is equal to nothing but dq by dt. So, using this I is equal to dq by dt and di by dt is equal to dtq by dt square, just substituting both these things into the equation again, we will obtain this equation, correct, that is L dtq by dt square plus dq by dt into R plus q by C is equal to Vm sin omega t, right. If you look at this equation clearly, it is nothing but similar to a damped oscillator which you have learned in your class 11th, that is waves oscillations, that chapter. Now, let us try to solve this equation. To solve this equation, we will need a solution. So, let us assume that solution is nothing but equal to q, which is equal to qm sin omega t plus theta. Therefore, dq by dt is nothing but qm omega cos omega t plus theta, and dtq by dt square is nothing but minus qm omega square sin omega t plus theta. Let us try to substitute everything. When we try to substitute everything, we will get this equation. If you look at this equation very clearly, we can directly implement the value of XL and XC directly. What is XL and XC? XL is inductive reactance, XC is capacitive reactance. Okay. After this substitution, we can directly obtain, so just substituting, rearranging the terms, we will get, we can put qm omega out, and therefore, we can obtain qm omega into r cos omega t plus theta plus xc minus xl into sin omega t plus theta, which is equal to Vm sin omega t. Let us try to divide it by, multiply and divide by r square plus xc minus xl whole square, which is basically capital Z, which is impedance. We will obtain this form. Okay. Now, if you look at this equation very carefully, in brackets, in bracket form, if we assume again r by z as cos phi and xc minus xl by z as sin phi, we can obtain this equation as v, which is equal to qm omega z into, this will be cos a cos b plus sin a sin b, which is nothing but cos b minus a. So, therefore, we can obtain this as equal to cos of omega t plus theta minus phi. Moving forward, so cos omega t plus theta minus phi can also be equated to Vm sin omega t, and using this comparison or basically writing sin omega t here, we can write it as equal to cos of omega t minus pi by 2. That thing being said, if we compare the two sides, we will obtain this as equal to Vm, which is equal to qm omega z. In the place of qm omega, we can also write it as equal to Im into z, because we know that V is nothing but equal to some value of I into some analogy of reactance, resistor. That resistor in the terms of LCR circuit is basically given by impedance. So, therefore, we write this equation as Vm is equal to Im into capital Z, and theta minus phi also, or basically this omega t plus theta minus phi is equal to omega t minus pi by 2, omega t gets cancelled, therefore, theta minus phi is nothing but minus pi by 2. So, therefore, theta is equal to phi minus pi by 2. Using both these things, we also know, so basically we obtained I, we obtained this equation using this equation number 3 here. So, this was the equation number 3 which we used, that is the solution which was assumed initially, as everything was being intact, the solution is correct. Therefore, I is equal to dq by dt, which is equal to qm omega cos omega t plus theta. In the place of theta, I just wrote phi minus phi by 2, and I changed this equation as sin omega t plus phi. I am nothing but Vm by z, and phi is nothing but equal to tan inverse xc minus xl by r. So, that is how the analytical solution is obtained, and it is in line with the solution we obtained using phasor diagram solution. Okay. Fine. So, I guess that is the end of this concept also. Let us try to dive into another very important topic, that is resonance. We will try to understand some application of this resonance also, so that we can understand why this topic is very important as far as the series LCR circuit or LC circuit etc. are considered. Okay. So, resonance. So, let us start understanding this resonance topic. So, an interesting characteristic of the series LCR circuit is the phenomena of resonance. The phenomena of resonance is common among systems that have the tendency to oscillate at a particular frequency. This frequency is called the system's natural frequency. Fine. If such a system is driven by an energy source at a frequency that is near the natural frequency, the amplitude of oscillation is found to be large. Listen to this line very carefully. If such a system is driven by an energy source at a frequency that is near the natural frequency, if it is near the natural frequency, the amplitude of oscillation is found to be large. So, it was being observed that if we are trying to oscillate near the natural frequency, then the amplitude will keep on increasing. This is nothing but called as resonance. Okay. So, a familiar example of this phenomena is child on a swing. Understand this example very carefully. The swing has a natural frequency of swinging back and forth like a pendulum. If the child pulls on the rope at regular intervals and the frequency of the pull is almost the same as frequency of swinging, the amplitude of swinging will be large. Okay. So, simple example. So, basically we are just trying to say that at the point let us suppose this is the natural frequency and this is the source frequency, right. So, if this source frequency is very close to this, the amplitude which is obtained is very high. That is only the explanation which we are trying to understand using this example here. Okay. So, let us try to understand this for an RLC circuit. So, let me try to make you understand this using a diagram and then we can close this session. In the next class I will try to explain this using the example for series LCR circuit. Okay. So, let us try to understand this. Let us suppose this is the omega value and let us suppose this is Im value, correct. So, let us suppose this is the natural frequency. The natural frequency is denoted generally by omega naught. Okay. So, let us suppose this is that value of omega naught here. Okay. So, in the first case scenario, let us suppose that we are in some sort of sequence in this form. Okay. And then in some sort of sequence we are assuming or we found that the amount of current being obtained or the amplitude of current, let me draw the diagram carefully. So, for the same value of omega, if we are calculating and getting the value of Im as different, it basically suffices to only one simple reason. For one AC source, the amount of omega which was obtained was very far from omega naught, and for the value of the voltage or the value of the source frequency which is very close to omega naught, the amount of amplitude obtained for current will be higher. Okay. So, this is the simple explanation regarding our electrical concepts. So, basically there will be two different sources, one will be having value omega 1, one will be having omega 2. The omega which is closer to omega naught will have an amplitude of the current which is higher than the another. Okay. So, that was a simple example regarding this. We will try to understand this using one of the example also which is explained in the subsequent slides. Let us not go to that point now. I will first derive some sort of sequences for resonance and then we can move forward in understanding why this thing happens. Let us try to mathematically calculate that in the next class. Okay. So, let me stop it here. So, the course progress for you, we have completed with the introduction. The next thing was AC voltage applied to a resistor, then phasor diagrams were being explained, then AC voltage applied to an inductor, then AC voltage applied to a capacitor. Then currently we are on the AC voltage applied to a series LCR circuit in which we are trying to understand a subtopic of resonance, so that we can understand this power in AC circuit, that is power factor. Power factor is again a very important concept as far as exams are considered. So, we will try to understand that, then we will understand LC oscillations and finally the use of transformers. Transformer is one of the basic explanations or basic what we can say application of this complete chapter which we are trying to understand. Okay. So, that thing being said, let me stop the discussion here only. Thank you so much.